So we've got something we've seen before here. It's the fundamental theorem of arithmetic, which says that every integer greater than 1 can be written uniquely as the product of prime numbers, give or take the order of their factors. 2 times 3, 3 times 2, we're going to call those the same thing. And if you remember when we talked about this earlier, I showed the uniqueness part. Right? I showed if a number has a prime factorization, then that prime factorization is unique. But we had to kind of put proving the existence of a prime factorization on hold. And the reason for that is proving existence requires strong induction, which is why we're taking it up again here. So how are we going to do this? Well, first, let's be clear what our proposition is. Our proposition P of n is n has a prime factorization where n meets the requirements of the theorem, right? Where n is strictly greater than 1. So what's our base case? Well, the smallest number in that set is going to be 2. So our basis step is going to be showing P of 2. In other words, that 2 has a prime factorization. Well, clearly it does. There's only one number in it. It's a product of one number, if you will. But 2 is itself prime, which gets us past the basis case, the basis step. All right, so what do we do next? So next we need to do the inductive step. And what's this going to say? This is going to say if every integer between 2 and I want to be careful, don't reuse a number, right? Let's say if every integer between 2 and n has a prime factorization, then so does n plus 1. So to do this, we're going to look at two cases. Right? Our first case is going to be the case where n plus 1 is prime. And our second situation is going to be the case where n plus 1 is not prime. In other words, where n plus 1 is composite. All right. Well, the n plus 1 case, we kind of get this one for free. If n plus 1 is prime, then just like we did back with when we looked at the basis step with n is equal to 2. If n plus 1 is prime, then n plus 1 is equal to itself. That's the product of a single prime number, and we're home free. Right? There's n plus 1 is its own prime factorization. So we can kind of put it that way here. Let's say n plus 1 is then its own prime factorization. All right, so how about this other side over here? What if n plus 1 is composite? Well, if n plus 1 is composite, that means there are two integers less than n, so let's write this. Therefore, there exist integers a and b. Both of these numbers have to be between 2, and they're going to be less than or equal to n, right? They both have to be smaller than n plus 1 itself, such that n is equal to the product of a and b. All right, this is where we're going to use our induction hypothesis. This hypothesis here that every integer between 2 and n has a prime factorization. Well, I don't know how big a is, but I do know it fits in that range between 2 and n, right? So both a and b have prime factorizations by the, and I'm running out of room here, I'm going to abbreviate a little bit, by the induction hypothesis. Well, and that's the end, right? Therefore, n has a prime factorization. Sorry, I'm going to jump way over here because I realize I need more room now. Equal to the prime factorizations of A and B. And that's it, right? That's what we need to show. We need to show that it existed, and we did. We kind of implicitly constructed it, right, by showing that it's the prime factorization of these two smaller numbers. And so that's it, right? That's the end of the proof. But I do want to take a step back and point out why strong induction was the way to go here. In plain mathematical induction, I'm restricted to only knowing that the next element down satisfies the induction hypothesis. And here, that was problematic because I know that these numbers A and B exist. The problem is I don't know how big they are, right? They may not be equal to n. They may be considerably smaller. Strong induction got me past that hurdle by letting me assume that everything less than or equal to n had the property that I needed. So I have a corollary here, and I think this may be the first corollary that we've seen, if I remember right. And what a corollary is it's a theorem, just like all the just like theorems and lemmas are, but corollaries are things that usually have a very short proof that follow directly from some other theorem, right? In a sense, there's something that we almost kind of get for free now that we know that other thing, right? And what this one says is that any integer greater than 1 is divisible by a prime number. Well, now I know that every integer greater than 1 has a prime factorization, right? The fundamental theorem of arithmetic says, give me a number greater than 1, an integer greater than 1, and I can write it as the product of prime numbers. Well, all of those prime numbers on that list are prime divisors of the original number. And we're done, right? You see, you almost kind of get it for free as a consequence of the previous theorem. All right, so that finally took a little time, but that finally completes the full theorem for us of the fundamental theorem of arithmetic. So, but I do want to look at some more examples of this strong induction. So in the next lecture, we're going to kind of go in a different direction and look at a geometric theorem that we can prove using this new method.